You guys, we're going to talk about thermodynamics. Okay. What we're going to look at is how gases can do work for us, or we can do work on gases. And you're thinking, gas doing work for us, or we doing work on gas? Who cares? But this is a big part of our lives because, for the most part, we all drive, we all use cars. And those cars are thermodynamic engines, essentially. We use gas to do work for us. And I know electric cars are a big thing, and they are coming. They predate the gas car, actually. But for the most part, we've been the beneficiaries of this process. And so we're going to be looking at certain things. So we're going to be talking about work done by gas. And one of the things we're going to look at a lot is the work done by gas inside something called a piston. So this is your cylinder right here, and this part moves up and down. It is called the piston. And what happens is the gas can do one of two things. The gas can do work by expanding, and if it expands, it forces the piston up. Or we can do work on the gas by pushing the piston down, and the gas gets compressed. And what happens in your car is actually those two things happen very, very fast all the time when your car is running. And so this is a thing in our lives.
I've talked a lot about how our change in internal energy of a system can be due to some heat being added to the system, or some work being added to the system or being done to the system. And I'm going to write it again the other way, just because you see it both ways. You could say that the change in internal energy could be the heat added to the system minus the work done by the system. So
what he meant to do here, he meant to write delta U here. And I think he made a note, but he messed that up. But that's okay. We all make mistakes.
There's two questions that might naturally spring up in your head. One is, how is heat added to or taken away from a system? And how is work done or done by or done to a system? The heat, I think, is fairly intuitive. If I have and we'll be more precise in the future of this, but I just want to give you the sense of what we're talking about. If I have some system here, some particles in some type of a canister, and it's at temperature, I don't know, let's say it's a temperature T1. I'll even give it a measure. Say it's at it's at 300 Kelvin. 300 Kelvin. If I want to add heat to this system, what I can do is I can place another system right next to it, maybe. Right next to it. Who knows what size it is. And it's got some particles there. But its temperature is much, much, much higher. So this temperature is going to be, this system's temperature, let's say T2 is equal to, let's say it's 1,000 Kelvin. I'm just making up numbers. So what's going to happen in this situation? You're going to have heat transferred from this second system to the first system. So you're going to have heat going into the system. Now, heat and work and even internal energy, this goes back to our conversation of macrostates versus microstates. Heat is changing the macro state of our systems. This system is going to lose temperature. The system is going to gain temperature. But we know what's happening on a micro level. These molecules are going to lose kinetic energy. These molecules are going to gain kinetic energy. How is that actually happening? Well, we assume that there's some type of a container here. Maybe it's a solid wall. These molecules are going to bump into that wall, are going to make the particles in that wall vibrate, and then they're going to make the particles in the green container's walls vibrate. And so when the green container's molecules touch the wall, they're going to bounce off with even more kinetic energy, with even more velocity, because of that vibration in the wall will push them back even further. So that's essentially how you get this transfer of kinetic energy, or this transfer of heat. But I think that's really intuitive. If we put this next to a cooler, a system with lower temperature, we would lose kinetic energy, or we would lose heat. There's other ways that we can do it. We can compress the container. Well, I don't want to talk about that just now, because that'll be touching on work. So, how can we add or subtract work to a system? And this one's a little bit more interesting. Let's go back to our piston example. Let's go back to just draw some lines here. So I have my container. Go. it's got a little movable sealing to it. That's my piston. And go back to the example, because what we're going to be dealing with, especially once I go into the pressure volume diagram, the PV diagram that I'm about to go into, we want to deal with quasi-static processes that are always close enough to equilibrium that we feel okay talking about macro states like pressure and volume. Remember that if we just did something crazy and the whole system is in flux, those macro states aren't defined anymore. So let's say we want to do a quasi-static process, so I'll have pebbles instead of one big rock. I'll draw the pebbles a little bigger this time. And I have some pressure, so that's my piston, and it's being kept down by these rocks. It's being kept up by the pressure of the gas. The gas is bumping into this sealing. It's bumping into everything. The pressure at every point in the container is the same. It's at equilibrium. Now, what happens in that example where I removed one rock from that? So let me copy and paste that. So if I remove one rock from this thing right here, copy and paste. So that's the same thing. Now let me remove a rock.
Yes, remove a rock. God, while we're young.
This top one was removed. What's going to happen? Well, I now have less weight pushing down on the piston, and I have a certain amount of pressure pushing up. The system, it'll very temporarily go out of equilibrium, but we did a very small difference in how much we're pressing down on it, so hopefully it won't be a huge change in our equilibrium. We'll stay pretty close to it. But we know from the previous example, instead of this thing flying up, it's just going to shift up a little bit. It's just going to shift up a little bit, right? When we do it, it's going to be like that right there. And let me fill in that part with black, because it's not like the space disappeared. So let me fill that in right there. So our little piston will move up a very small amount. And what I claim is when this happened, when I removed this little pebble from here, the system did some work. And let's just think about that. So work, according to the definitions that you learned in first year physics, and when you just do using classical or dealing with classical mechanics, you learn that work is equal to force times distance. So if I'm claiming that when this piston moved up a little bit, when I removed that pebble, I'm claiming that this system here did some work. So I'm claiming that it applied a force to this piston, and it applied that force to the piston for some distance. So let's figure out what that is, and if we can somehow relate it to other macro properties that we know reasonably well. Well, we know the pressure and the volume, right? We know the pressure that's being exerted on the piston, at least at this point in time. And what's pressure? Pressure
Just write a P,
is equal
dude.
to force per area.
There we go.
Force per area. Right? So the area, remember this piston, there's some, you're seeing it from the side, but it's a kind of a flat plate or a flat ceiling on top of this thing. And now what distance did it move it? Let's just call that, I could blow it up a little bit. Let me, it moved it some, I didn't draw it too big here, some x. Some distance x, right? So this change, it moved it up some distance x there, right? So what is the force that it pushed it up? Well, the force, we know it's pressure. The pressure is force per area. So if we want to know the force, we have to multiply pressure times area. If we multiply both sides of this times area, we get force. So we're essentially saying the area of this little sealing to this container right there. It could be, I could draw it with some depth, but I think you know what I'm talking about. It has some area. It's probably the same area as the base of the container, right? So we could say that the force being applied by our system, let me do the new color, the force is equal to our pressure of the system, pressure, times the area of the sealing, of our container, of the piston. Now that's the force. Now what's the distance? The distance is this x over here. The distance is, I'll do it in blue. It's this change right here. I didn't draw it too big, but that's that x. Now let's see if we can relate this somehow. Let me draw it a little bit bigger.
can't handle any more, guys. So, force equals pressure times area times X. What he's going to do is he's going to take force here, which is PAX. He's going to throw it in right here. So instead of force, he throws in PAX. It goes in right there, right? Area is length times width times X, which is a height. This AX is length times width times height, right? So where he's going with this, he's going to multiply by a distance, is he ends up with volume. And I think once we get down there, and I just want to strangle him, I'm watching his cursor fly around, as he gets work equals PAX, boom, 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 work equals pressure times volume. When he's talking about the fact that gases can do work on us, for us, or we can do work on the gas itself, and this is a thing. Okay.
Repercussion here. So we can rewrite our internal energy formulas. So for example, we can write internal change in internal energy is now equal to heat added to the system plus the work, minus the work done by the system, minus the work done by the system. Well, what is the work done by the system? Well, it's the pressure of the system times how much the system expanded. Right? In this case, the system is pushing these marbles or these pieces of sand up. It's doing work. If we were doing the other way, if we were adding the sand and we were pushing down on our little canister, we would be doing work to the system. So this is the situation where I'm doing here, where I'm removing the sand and the piston goes up. Essentially, the gas is pushing up on the piston. The system is doing the work. So if we go back to our little formula, that internal energy is heat minus the work done by system, so done by, then we could write this as this is equal to the heat added to the system, heat added, minus this quantity, the pressure of the system, times the change in volume. It is interesting. If the volume is increasing, then the system is doing work. And this applies, we're going to talk a lot more about engines in the future, but that's how engines do work. They have a little explosion that goes on inside of a cylinder that pushes up on the piston, and then that piston moves a bunch of other stuff that eventually turns wheels. So when the volume increases, you're actually doing work. So I'm going to leave you there in this video. In the next video, we're going to...
I can't. So the equation he was using, delta U equals Q plus W. This is known as the first law. And it says the internal energy of, you can read it, okay? The system is our piston, and then whatever the gas is. Right? Now we're going to make some assumptions here that there's no friction, and that we can add heat to or take heat away. Right? So here's what happens. So work is equal to negative PV. Work done by a gas or on a gas. These are your two options. Okay, if we heat the gas will expand. It will push the piston up. We can say that there is work done by the gas. When work is done by the gas, you get a positive volume change because now you have a larger volume than you previously did. But work by the gas is negative because when you take this positive volume and multiply by this negative sign, you get a negative work. So work done by the gas is negative. This is weird, but here's what happens. We give heat to the gas. It's then going to do work to push the piston up. And what happens is, by doing that work, the gas then loses energy. So, if the gas does work, it's called negative work. Now, positive is when if we have the piston and we press it down, we compress that gas, right? There is now a negative volume change because now you have a smaller volume than you previously did. When you take that negative volume and you multiply by negative P, you get a positive. So if we do work on the gas, it is now positive. Okay? This is hard to keep track of. This has actually changed from what it used to be. So pay close attention. You may need to write some things down.